What if the fastest thing in the universe is not a speed limit at all, but a measurement boundary? You are receiving this transmission from the year 2100. What you are about to hear is not a rejection of the science your era built. It is an analysis of what that science was reaching toward and what it could not yet see. We have been monitoring the intellectual history of your century for some time now, and of all the beliefs your era held with the greatest confidence, few were held more tightly or more understandably than this one. The speed of light cannot be exceeded. Nothing in the universe travels faster. It is a hard ceiling on physical reality itself. We begin there, not to dismantle it immediately, but to examine it carefully, the way you might examine a wall you have lived beside for so long that you stop noticing its exact dimensions. In the early 21st century, the speed of light was treated as one of the most sacred numbers in physics. 186,000 miles per second, approximately 300 millimeters per second in vacuum, denoted as c, constant, universal, inviolable. Entire frameworks of reality were constructed around it. Special relativity, the cosmic speed limit. The reason why, as your physicist described it, nothing with mass could ever reach it, let alone exceed it. Energy requirements would become infinite as any massive object approached c. Time would dilate toward a standstill. Length would contract toward zero. Causality itself, the relationship between cause and effect that your era considered the backbone of rational reality, would collapse if the limit were breached. These were not guesses. They were mathematically precise conclusions derived from equations tested across more than a century of experimentation. GPS satellites required relativistic corrections to function. Particle accelerators confirmed time dilation directly. The predictions were not approximately right. They were precisely right to many decimal places, and they were correct within the framework that produced them. That last phrase is the one we will return to many times in this transmission, within the framework, because what your era rarely examined with full philosophical seriousness was where the framework itself came from, what assumptions it rested on, and whether those assumptions were themselves laws of nature or decisions made at an earlier stage of understanding that had never been fully reopened. Physics in your era was extraordinarily successful. It built satellites, mapped genomes, split atoms, and modeled the first moments after the universe began. It gave your civilization tools of almost incomprehensible power. These were genuine achievements. We do not diminish them from this distance. The humans who built those frameworks were extraordinary. They operated at the edge of what was knowable from where they stood. But every framework carries invisible walls. And the hardest walls to see are the ones you built yourself, because they feel less like walls and more like the shape of the room. Consider what the speed of light actually is. At its foundation, strip away the equations for a moment. Strip away the history and the textbooks. Ask only this: what is being measured when you measure c? You are measuring the rate at which electromagnetic disturbances propagate through the structure of spacetime as understood in your era, not through some abstract mathematical space, through a specific physical medium, the quantum vacuum, the lowest energy state of the fields that constitute your universe, a medium with specific properties, a specific permittivity, a specific permeability, and those properties, taken together, determine how fast light moves through it. Your instruments measured this within that medium. Your theories were calibrated against the behavior of that medium. Your conclusions were precise and valid descriptions of how electromagnetic radiation behaves inside a particular physical configuration of reality. This is not a flaw. This is how science works and how it should work. You measure from where you stand. You construct theories that account for what your instruments detect. You validate against experiment. You refine. But here's a question your era rarely asked with full seriousness. What if the medium is not fixed? What if the quantum vacuum, the structured emptiness to which light travels, is not the unchanging background stage on which physics performs, but is itself a physical object with a history, a possible range of states, and properties that are contingent rather than necessary? Einstein himself gave you part of this. He told you space-time was dynamic. It could curve in the presence of mass and energy. It could stretch. The expansion of the universe, which your cosmologist confirmed and measured with extraordinary precision, meant that distant regions of space were receding from each other at rates that appeared to exceed c when measured across cosmological scales. Your physicists acknowledged this openly. They explained carefully that it was not objects moving through space faster than light. It was space itself expanding. The metric was stretching, and because the limit applied to motion through space, not to the expansion of space, there was no contradiction. They were right to make that distinction. The logic was sound within the framework. But notice what that distinction implies. If you follow it far enough, the limit was never a statement about the universe as a whole. It was a statement about a specific relationship. Objects moving through local space-time relative to other objects in that same local space-time. The moment you ask what space-time itself can do, what the metric can do, what the vacuum structure can do, you are asking a different class of question, and that different class of question does not have the same answer. Your era understood this in cosmology. You accepted that there were regions of the universe permanently beyond your observable horizon, not because nothing existed there, not because physics broke down there, but because the geometry of expanding space made information exchange between here and there permanently impossible from your current vantage point. You accepted the concept of the observer-dependent horizon. You built entire cosmological models around it. You simply did not carry the implication fully into your understanding of physical law at smaller scales. Here is where the analysis becomes more precise and more unsettling. The laws of physics, as your era described them, were laws of relationship. Specific relationships between specific quantities, as measured by specific observers, in specific reference frames. This is what relativity itself told you. There is no privileged frame. Every measurement is relative to the measurer. Motion has no absolute meaning, only meaning relative to something else. And yet, the speed of light was treated as an absolute, a universal constant, the same for all inertial observers regardless of their relative motion. Your physicists were aware of this apparent asymmetry. They resolved it by demonstrating that c is invariant across reference frames, that this invariance is in fact the deep principle from which the rest of relativity flows. They were correct. The invariance of c is not an assumption. It is an empirically confirmed fact about your universe, tested in every precision experiment your era could devise. But there is a question underneath that fact that the fact itself does not answer. Why is c invariant? What makes it so? The standard answer in your era was essentially definitional. C is invariant because it is a property of space-time geometry itself, baked into the structure of the Minkowski metric that describes flat space-time. It is not that light happens to travel at c. It is that c defines a relationship between space and time at the most fundamental geometric level. Light travels at c because massless particles must travel at the speed that space-time geometry singles out as the invariant one. This is a satisfying answer. It is also, if you examine it carefully, a description of a specific geometry. The Minkowski metric is a choice, a well-motivated, experimentally validated choice for flat space-time in the absence of gravity, but a choice nonetheless, a mathematical model selected because it fits the data. What happens when the geometry is different? What happens in curved space-time? What happens if the vacuum itself is in a different state? Your era had fragments of answers to these questions scattered across disciplines that rarely spoke to each other with full fluency. Quantum field theory and curved space-time showed that the behavior of fields changes when the geometry changes. The Unruh effect demonstrated that what one observer calls empty vacuum, another accelerating observer detects as a thermal bath of particles. The Hawking radiation prediction showed that the geometry near a black hole horizon transforms the vacuum state in ways that produce real particle emission. Same physics, different geometry, different vacuum state, different observable reality. Your era knew this. It was not hidden, but the implications were treated as exotic phenomena relevant only to extreme situations. Black holes, the early universe, regions of intense space-time curvature, not as hints about the nature of physical law itself. What the paradigm shift of the following decades required was a willingness to take those exotic edge cases seriously as windows into the structure of the rules rather than exceptions to them. Consider for a moment the history of constants in physics. Your era treated the fundamental constants, c, the gravitational constant, Planck's constant, the fine structure constant, as fixed features of reality, numbers that simply were what they were, unchanging across all of space and time. Some of your cosmologists began to question this, not loudly, not with institutional confidence, but with mathematical seriousness. There were observations suggesting the fine structure constant might have been slightly different in the early universe. There were theoretical frameworks in which constants could vary across different regions of a multiverse landscape. There were models in which the laws of physics themselves were better understood as local features of a particular vacuum state, rather than transcendent truths. These ideas faced enormous resistance, partly because the experimental evidence was ambiguous, partly because varying constants created serious theoretical problems that were not easily resolved, but partly also because the idea itself was philosophically uncomfortable. If the constants are not constant, what is left that is truly fundamental? What can you trust? This discomfort is understandable. It is human, but it is worth examining, because it is precisely the kind of discomfort that marks a framework protecting its own boundaries. The assumption that constants must be constant is not derived from experiment. It is not logically necessary. It is a prior, a background belief so deeply embedded in the structure of physics that it was rarely stated explicitly because it did not need to be. It was the water, and like all water, it was invisible to those swimming in it. Your era was not unique in this. Every mature scientific framework has its water, concepts so foundational that they feel less like assumptions and more like the shape of thought itself. Before Copernicus, the Earth's central position was not an assumption astronomers made. It was simply the way the universe was arranged. Before Darwin, the fixity of species was not a belief biologists held. It was a structure within which biology operated. Before quantum mechanics, the determinism of physical law was not a philosophical position physicists defended. It was the implicit contract between physics and reality. In each case, the framework that followed did not erase its predecessor. It revealed the predecessor as a special case, valid within a domain, limited at its edges. Newton did not disappear after Einstein. Newtonian mechanics remained exactly as useful as it had always been for the situations it was designed to describe. It simply ceased to be the last word. We are not saying Einstein will disappear after whatever framework your century was beginning to approach. We are saying the pattern is consistent, and patterns across the history of knowledge are worth taking seriously. Let us now speak about something your era called the Alcubierre metric. In 1994, a physicist named Miguel Alcubierre demonstrated mathematically that general relativity does not prohibit a specific kind of space-time geometry in which a region of flat space is enclosed within a distortion that contracts space in front of it and expands space behind it. An object inside this bubble would not be moving through space faster than c. The space around it would be moving, carrying the object along. Your physicists were careful to note the theoretical problems with this construction. The energy requirements were absurd, involving negative energy densities in magnitudes that appeared physically unrealizable. Causality questions were serious. The bubble could not be activated from inside. There were issues with quantum stability that had not been resolved. But notice what the Alcubierre metric demonstrated even in its problematic form. The mathematical structure of general relativity. The same structure that gives you the speed of light as a limit on motion through space does not prohibit what might be called effective superluminal displacement through manipulation of the space itself. The framework that encodes the limit also contains, within its own equations, geometries that work around the limit by operating on the substrate rather than the objects. This is not a loophole in the naive sense. It is a structural feature, and structural features of a framework reveal the shape of what the framework is actually describing. What the Alcubierre metric revealed, in the language your era could access, was that c is a limit on a specific variable in a specific equation under specific conditions. Change the conditions, and what seemed like an absolute boundary reveals itself as a boundary of a particular operational regime. Your era also encountered something called quantum entanglement. Two particles, correlated at the quantum level, exhibit coordinated behavior regardless of the distance between them. Einstein called it spooky action at a distance and considered evidence that quantum mechanics was incomplete. Your era confirmed it experimentally, an increasingly rigorous test that closed every proposed loophole. The correlations were real. They were instantaneous in the sense that no local hidden variable could account for them within any framework that preserved both locality and realism. Your physicists were careful to point out that entanglement could not be used to transmit information faster than light. The correlations were real but random. You could not control what outcome a measurement would produce, only that two distant outcomes would be correlated. Without a classical channel to compare results, no information transfer occurred. This was correct, and the inability to use entanglement for superluminal signaling was not a technicality. It was a deep feature connected to the structure of quantum measurement itself. But consider what entanglement nonetheless revealed. There is a level of physical reality at which spatial separation does not function the way it appears to from the classical perspective. Two particles that are entangled are, in some sense that is not fully metaphorical, not fully separate. The quantum state is non-local. The correlations are non-local. The universe, at the quantum level, does not respect the sharp boundaries between here and there that classical physics assumed. Your era knew this. It was one of the most discussed and least resolved features of quantum foundations. The debate between different interpretations of quantum mechanics, Copenhagen, many worlds, pilot wave, relational cubism, was in large part a debate about what the non-locality of entanglement meant for the nature of reality. Most working physicists set the interpretive questions aside and used equations. This was pragmatically rational. The equations worked, but it meant that the deepest questions about what quantum non-locality implied for the structure of space, time, and causality were left hanging, acknowledged but not resolved. The resolution, or more precisely the framework within which a resolution became possible, required taking seriously that space-time itself might be better understood as emergent from something more fundamental, that the sharp divisions of here and there, now and then, might be features of particular organizational level reality, rather than the bedrock beneath everything else. In your era, the word emergent was well understood in some contexts. Consciousness emerging from neurons, wetness emerging from the collective behavior of water molecules, temperature as a statistical property of molecular motion rather than a feature of any individual molecule. You understood that higher level descriptions could be real and accurate without being fundamental, that complex properties could arise from simpler interactions in ways that could not be predicted by examining the components in isolation. But the application of emergence to space-time itself, to the metric, to the geometric structure within which C is defined, was not yet fully developed as a research program with institutional momentum behind it. The ideas existed. Physicists like Ted Jacobson had shown that the Einstein field equations could be derived from thermodynamic principles applied to horizons, suggesting that gravity, and by extension space-time geometry, might be a thermodynamic emergent phenomenon. Work on holography and the AD/CFT correspondence suggested that a gravitational space-time could be equivalent to a quantum system without gravity in one fewer dimension. These were not marginal ideas. They were among the most discussed topics in theoretical physics in the early 21st century, but their full implications for the question of fundamental limits had not yet been assembled into a coherent alternative framework. That assembly is what the following decades began. We speak of it carefully, not because it is sensitive, but because describing the future to the past is an exercise in selecting the right altitude. Too much detail obscures rather than illuminates. What we can say is that the question changed. Your era asked, can anything travel faster than light? The question that followed asked, what exactly is traveling? Through what exactly? And is a structure that through a law of logic or a contingent fact about particular physical configuration? These are not the same question. And different questions produce different kinds of answers. The first question, asked within the standard framework, has a clear answer. No, nothing with mass can reach C, and no local signal can exceed it without violating causality in ways the framework prohibits. The second question, asked about the framework itself, opens into territory that your era was only beginning to map. Whether that territory contains what might be called practical traversal of the restrictions your era called absolute is not something we will state directly. It would be irresponsible to imply specific technologies or capabilities in this context. What we will say is that the relationship between the question and the answer changed when the question changed. And the change of question was itself the breakthrough. This is almost always how it works. The barrier is not the data. The barrier is the question. Newton's mechanics were not broken by new data that contradicted them. They were contextualized by a new question, asked by Einstein, about what happens when you take the invariance of C seriously as a starting point rather than a conclusion. The old data was still explained. A new range of phenomena became explainable alongside it. The same structure tends to repeat. Your era's understanding of the light speed limit was not broken by experiments that contradicted it. The limit remained valid within its domain, as Newton remained valid within his. What changed was the question being asked about the domain itself. What is this domain? How large is it? What lies beyond its edges? Are the edges the edge of reality or the edge of a particular description of reality? Those questions were alive in your era, present in the literature, discussed in seminars and conference halls, and in the papers of physicists who were willing to work at the uncomfortable edges of what their framework could accommodate. What they needed was not more data within the existing framework. They needed a conceptual shift that would let them see the framework from outside it. That shift takes time. It takes generations. Often, it takes accumulation of discomfort with existing tools, of anomalies that resist explanation, of young researchers who did not grow up with the old framework's invisible assumptions baked into their thinking. By 2100, that accumulation had happened. The shift had occurred. We speak from the other side of it. Looking back at the moment before, the way you might look back at the world before discovery that now seems obvious in retrospect. Nothing about your era's science was foolish. Nothing about the belief in C as an absolute limit was irrational. It was the most precise, most tested, most carefully validated position available given the tools and the conceptual language of your time. But certainty, even justified certainty, is not the same as completeness. And incompleteness is not failure. It is a natural condition of knowledge at any moment in its development. Every era of science is complete enough to be useful and incomplete enough to be superseded. This is not a tragedy. It is the mechanism by which understanding grows. The universe, it appears, does not place hard ceilings on its own depth. Every layer of reality that becomes fully understood reveals another layer beneath it, with its own structure, its own properties, its own surprises. The light speed limit was a feature of one such layer, a real feature, a precisely described feature, a feature that remained valid at that layer even as the layer below it began to be understood. What you called the absolute was the most precise description possible at a particular resolution of investigation. And resolution, in science as in perception, determines what you can see. Increase the resolution, and the smooth surface reveals texture. The solid boundary reveals its contingency. The final answer reveals itself as a very good answer to a slightly different question than the one that ultimately mattered. We transmit this not to disturb your confidence in the science of your era. That confidence is earned and appropriate. We transmit it because the question of whether a limit is a law of nature or a law of your current description of nature is always worth asking. And the habit of asking it, the intellectual posture of holding certainty gently, of knowing that your best understanding is your best current understanding rather than your last one, is perhaps the most valuable scientific disposition of all. Your era was not wrong. It was early, and being early in the history of a civilization that is still learning what it is capable of is not a criticism. It is a position on a trajectory, one that, from here, we can see was pointing in the right direction all along. Signal stable. Archive updated. Transmission paused.